interaction. Yes, clean steel production, scale and descaling, grade and practice development, thermomechanical processing, and a whole host of others. Those programs within the center have also leveraged some very substantial programs outside of the center related to funding projects from DOE and the Defense Logistics Agency. Many of these have focused on sensor development using fiber optics. The one I'll talk to you about is grid interactive steelmaking with hydrogen, and a little bit about the idea is intelligent dynamic EAF optimization. Just to start off, one of the big sensors areas that we are involved in is fiber optics. We are developing high temperature sensors based on fiber optics that do interferometry, Bragg grading for temperature and strain, something called optical frequency domain reflectometry, which can use Rayleigh-Bernoulli or Raman scattering to get near continuous temperature or strain measurements. And we're utilizing different types of fibers depending upon the application. They may be single mode, multi-mode, or coreless fibers. Some of these fibers have the capability of surviving environments up to 2200 centigrade. To give you some idea of what some of these, I locked up. I crashed. So let's see what happened here. Hold on. Wow. Stop share here for a minute. Sorry about that. We'll try to get back on real quick. Don't know what happened.
Okay, some technical difficulties. In a moment, we're going to start again. Here we go.
Okay. So I'm going to step forward here real quick and catch up where I left off here. My apologies. So one of the things that we are able to do is use single fibers. I got to shrink some of this stuff. Can you see all right?
Yes.
Okay, I got to move some of this stuff out of the way. Sorry about that. There we go. All right. So one of the things you can see here is a single fiber that is giving real-time temperature information. It has been placed inside a mold, and that fiber is woven back and forth. And we can collect temperature at very high resolution, about 0.5 millimeter along the length, and actually map temperature. It's a really interesting technology for exceptionally high resolution thermal mapping. And you can see here some of the relationships that we can see between temperature and shell thickness on a solidified shell on a mold. And even to the right, the thermal maps that you can obtain by using a single fiber. And here it's resolving high-level details of oscillation mark formation in the continuous casting process. This also shows the dynamic capabilities of these fibers to measure strain. And this fiber is being interrogated in real time to measure dynamic strain. Once again, a single fiber, we can get strain measurement points entirely along the length of the fiber. Another technology that we're using is fiber Bragg grading technology with these fibers. And these fibers can be constructed of sapphire single crystal fibers, and the fiber Bragg grading sensors can be etched on them with a laser, and these gratings will reflect based on their temperature. Their frequency will reflect it based on their temperature or strain that is experienced by the fiber. The beauty of these types of fibers is that they can service exceptionally high temperatures. In fact, this is a fiber embedded in a commercial submerged entry nozzle where we're measuring the temperature at 3 points along the fiber length through a preheat cycle on the SEN. These fibers can exist and do temperature measurements. We've measured them as high as 1800 centigrade. So they are exceptionally valuable for the steelmaking environment. We're also mapping a whole variety of different processes, electric furnaces. We're looking at heat temperatures on spray-cooled shells using fiber technology, and instrumenting bottom anodes on DC furnaces to measure temperature to actually track the bottom wear in the furnace. In fact, this video shows a dynamic playback of the temperature profile, both average and these little bumps or undulations that you see. The bumps in the temperature are actually directly related to the joule heating of the pin. And that joule heating is a direct measure of the local current density flowing through that pin. And so we can map where the arc is striking the bottom of the furnace and also map the average wear of the pins. If you look at the left, we're actually using a thermal model to track each individual pin length through that instrumented pin and ultimately tracking that through the entire life of the furnace. This is all being done with fiber optics. It's really exciting applications. Another area where we're doing sensing is in the area of high temperature Raman analysis for slag chemistry and structure detection. And we've built some high temperature Raman probes that are capable of delivering a laser excitation signal and then collecting the resultant Raman emissions from the slag. And we can do that at elevated temperatures. The structure of slags, particular silicate slags, are polymeric in nature, and the individual chain length of those silicates can actually impart a vibration that is detected by Raman that has a specific peak wavelength. When we extract the Raman spectra from this signal, we can actually deconvolute the peaks and represent the Q0 through Q4 structures in the silicate region of the Raman spectra and relate that directly to the structure. And ultimately that relates to the basicity, silica content, and even viscosity of the slag. So this probe can actually do these types of extraction measurements in real time. What's more exciting is that we've been able to show that these, oh, and I crashed again. What's going on? These probes can actually be used in the mold, and the measurement of Raman spectra can be done in real time. And I'm going to have to stop and reboot again. My apologies.
Don't worry. Okay.
See if I can get this to play again. All right. So you can actually see a video of us using the probe in the mold at an operating steel plant. This happened to be SSAB in Mobile, Alabama. And to the lower right is the continuous signal.
Doctor, sorry, can you share the...
Oh, yes, absolutely. Sorry.
There we go.
Okay. So the other kind of work we're doing is we do inclusion surveys for clean steel and evaluate the evolution of inclusion morphologies over time. These studies are done largely in our laboratory where we have upwards to 500-pound steel melting capacity in an air melt induction furnace. And we've actually been able to track the evolution of inclusions and their behavior from their inception in the electric furnace all the way through the final product. All right. Please bear with me. This is apparently very unstable and it crashed again. So I can't actually. Are you okay if I hold for a minute and try to switch machines?
Yes, it's no problem.
My apologies for this. I don't know what's going on with the machine, but it must be an interaction with the Zoom.
Well, Dr. O'Malley have some technical difficulties. Please waiting for these technical difficulties be solved. In a moment, we're going to start again with the conference. Thank you.
Recording in progress.
Okay, as I said before, Dr. O'Malley some technical difficulties. So in a moment, we're going to start again. Okay.
Sorry, are we showing now?
Yes.
Okay, good. Different machine, so hopefully this one will be more stable. My apologies for the technical difficulties. Um, what I was hoping to show you was some of the inclusion analysis work that we've been doing, and I'll go through this somewhat quickly. And some of the work we do in thermomechanical processing as well. Uh, We utilize various tests to develop constitutive models for flow stress, study both dynamic recrystallization and static recrystallization using a quenching deformation dilatometer that allows us to do this work. And then we develop the constitutive equations that feed into the appropriate forming models using finite element to actually track the evolution of shape and defects in product. And we've had great success mimicking industrial processing. This happens to be a beam rolling at Nucor Yamato, where we were able to successfully predict the defects formation associated with one grade of steel that has different flow characteristics than a traditional A992 steel. One of the things we're excited about is we are a member of the EPICS consortium. EPICS is the electrification of combustion processes that is headed out of Arizona State University. But we are slated to be the steel electrification testbed site. And for that purpose, we've actually uh, provided access to facilities where we have our pilot scale rolling mill, and we will be installing various uh, testing heating technologies, including plasma heating, induction heating, and hydrogen as alternative heating methods for the hot rolling of steels. But really, what I wanted to talk to you about today is our program on grid interactive steelmaking with hydrogen. The premise of this program is to develop a methodology by which we can use hydrogen as a reductant to produce steel through the direct reduced iron electric furnace path, but to develop a process in such a way that we can dynamically switch between hydrogen and natural gas based on the availability of green energy through renewable energy sources. So the whole concept here is that we can produce materials that are required as virgin iron units for the EAF as needed through natural gas, but take advantage of the availability of low-cost hydrogen when it is generated at off-peak periods. And this program has many partners in it and actually has many parts to the program to try to understand the knowledge gaps associated with not only the production of DRI in hydrogen and natural gas swing reactions, but also in the utilization of hydrogen DRI with its absence of carbon in the electric furnace and the impact on melting behavior. So you can see we have partners with Arizona State University, equipment supplier Danieli, ArcelorMittal, Steel Dynamics, Gerdau North America, Nucor, two gas suppliers, Linde and Air Liquide, and the National Renewable Energy Laboratory, or NREL, which is a government facility who has focused primarily on the techno-economic analysis. So our goal here is to, of course, try to move down the carbon triangle and utilize EAF processing, hydrogen DRI production to produce a low carbon footprint steel. The path here is a variant of a scrap feed path where we use scrap to feed the electric furnace, which is also a low emission route. And we utilize the virgin iron units to offset the accumulation of tramp element residuals in the scrap. Within our program, we actually have several stages of research. We've got laboratory scale research studies looking at the mixed gas reduction reactions in lab reduction trials. We're looking at melting trials in the lab using carbon and carbon-free DRI. We're investigating the uses of hydrogen plasma as an accelerant for the direct reduction kinetics. And we're developing these kinetic models to utilize both in commercial scale up and in pilot scale operations. For the pilot scale part of this, we actually constructed a DRI reactor that is capable of producing actually about 2.5 tons a week. And to produce enough DRI based on hydrogen and mixed gas that we can actually evaluate in production environment its melting behavior. And then finally, we've done full-scale production trials in the plant environment to produce DRI at commercial DRI production sites with low and high carbon, but also to melt these materials in various production facilities. So our kinetic models are essentially gas-solid reaction kinetic models that are employed to describe the kinetics of reduction based on mixed gas reduction and hydrogen reduction. And this model then becomes the heart of a reactor model that is utilized to model the overall pilot and production scale reactors. We've done a lot of work comparing these reduction reactions to laboratory and pilot measurements, and have a lot of faith in these models, and they've worked very well. The other thing that we've looked at is the physical experimentation of the melting behavior. As I mentioned before, DRI, when it's produced by natural gas, actually contains carbon, and oftentimes will contain upwards to 2.5% carbon. And that carbon actually has benefits in the melting behavior of DRI because the carbon in the pellet will react with the unmetallized portion of the oxides to liberate carbon monoxide gas. That carbon monoxide gas actually serves to agitate the bath and enhance the melting behavior. And we've done experiments in the lab to show this. This is actually one of our experimental lab setups where we actually will do the melting studies for DRI. We embed a thermocouple into a pellet, plunge it, and then monitor its temperature rise and melting behavior. We can actually interrupt and pull it out to look at the intermittent shell growth. You'll notice in the lower right, some of these shell growths actually have blowholes in them, and this is the carbon monoxide evolution that actually serves to agitate as the pellet continues to metallize in the presence of the molten steel or slag. If you look at these traces of measurements, the heating rates actually you can see go up as the carbon content of the pellet goes up. And this is because of that gas evolution reaction. Now, the reaction itself is endothermic. And it's very clear, though, that the endothermics are well overcome by the enhancements in the heat transfer by the gas evolution reactions. Here you can see the 3.5% carbon or 3.7 carbon heating and melting rates are a lot faster than the 1.3 and faster than the hydrogen pellet, which has 0 carbon in it. We also have done these types of measurements in steel and slag systems, since the melting of DRI can occur in steel, in slag, or at the melt-metal interface. So these models have been developed to predict the melting behavior, and we then use those in larger scale models to characterize the melting characteristics of these materials. We also model the gas generation in the pellet, and the off-gassing in that pellet is then tied to the heat transfer, and we've developed some heat transfer correlations to relate the volumetric gas evolution to the enhancement of the heat transfer coefficient and convection. We're also modeling more complex situations with multiple pellets and pellets at the slag metal interface to study how these melting behaviors might occur in these different environments. So in the lab, we've done a lot of this type of work, but we've also built a pilot plant, and this particular pilot plant was constructed on in a facility in at Hazen in Golden, Colorado. One of the reasons we put it on site there is that Hazen had the capabilities of handling hydrogen safely. Plus, they had this remote bunker that could be used to house the reactor. It's a 3-story tall bunker, and the reactor tower is inside of it with all the gas handling and recycling equipment. The lower left shows a schematic of the reactor. It is a countercurrent reactor where pellets are fed in at the top through an interlock system. Preheated gases are fed in the bottom. The gases go up and then exit the system. The pellets go downward and then exit the system. These pellets are entirely sealed so that they can be packaged in drums without any exposure to air. The off-gas system goes through a condenser to take the water out of the system, and the hydrogen that is remaining then recycles back into the reactor. So it's a fairly nice complex reactor. It was designed to produce well in excess of 1 ton a week of material, which allowed us to get enough material to do bulk melting trials in commercial environments. This is just a step through the reactor system. The lower left is the ore pellet feed system. We have a conveyor system that takes it up to the top of the reactor, feeds it in the top, and feeds it into the shaft. That shaft then has an interlock to take it into the hydrogen environment safely, and then passes down 1 story through a heated zone in the reactor, and then through to the bottom where we have a discharge system and the gas injection component of the system, where we have the gas preheater injecting the hot gas that can be hydrogen, natural gas, or a mixture of the two. And then the exit system, we have a cooling system that allows the DRI pellets to be cooled and extracted and then packaged in drums. This is actually what our DRI looks like. It actually turns out to be very strong and has good handleability and has in excess of actually of 98% metallization. One of the things that's kind of interesting is if we look at laboratory reduction trials, there's been a lot of discussion about pellet swelling in the presence of hydrogen. We've actually seen it in our laboratory experiments, but when we go to the production environment, the processing path of the gas and the solids going through their heating path and their gas reduction path actually do not show the same swelling characteristics. And it just highlights the actual importance of having pilot scale tests so that you don't develop some erroneous concepts of what's going to happen in the reduction of these materials. We've actually operated these plants in 4 campaigns. Each campaign operates for about 1 week. And we have done pure hydrogen in various configurations, and then hydrogen and natural gas as well. And the pilot plant trials were, totally successful. I will tell you that we early on had some issues. The very first trial, we actually had very cold weather in Golden, Colorado, and the temperatures were so low that we froze the water recycling system. And so we didn't get as high metallization and hydrogen utilization as we hoped. In the second campaign, we did that one in the spring, and that worked a lot better, and the recycling systems worked. We had some bridging problems early on, and we were able to resolve that by using some techniques used in the commercial operation, is lime coating of the hematite pellets. And that actually successfully, in conjunction with the control of the temperatures, controlled the bridging of the pellets. We've modeled the reactor using various types of models, and these reactor models have been compared to the experimental measurements and we've gotten from the pilot plant operation. This happens to be a COMSOL model for the gas-solid exchange reactions and the countercurrent flow of the solids downward and the the gases upward. And we were able to actually get better than 90% accuracy on these predictions. So they actually have been very successful then at developing models for scaling up the hydrogen reaction in a commercial scale reactor. And this is pretty important because these scale ups are important because it turns out when you reduce with hydrogen, the reactions are entirely endothermic, and you have to consider the endothermicity in the transfer of heat and energy into the reactor bed. Now, that varies from conditions you see with natural gas, where you actually get some exothermic reactions in the bed that actually contribute to the heat transfer. Now, with that inefficiency of hydrogen transport, we also had another program that was exploratory to determine whether we could utilize plasma or ionized hydrogen as a reductant and what it would do to the reaction kinetics. And so we set up a small scale reactor to study this, and in fact, found that when we ionize the hydrogen, split it into monatomic and or ionized states, the reaction kinetics are enhanced. The other thing that happens is that the ionized or dissociated species results in the reaction with the ore to metal being exothermic instead of endothermic. And so it actually results in transferring heat to the bed more efficiently. So one of our goals ultimately would be to take these very high cost conventional heating systems here that heat the hydrogen and natural gas and replace it with a plasma heating system that could be utilized to efficiently heat the gases, dissociate and ionize to enhance the reaction kinetics and eliminate these very costly heat exchanger bundle systems that are super alloy and extremely expensive. I mentioned that we also did plant trials, and this actually shows a comparison of carbon and hydrogen DRI being fed into the slag metal system in this case, an LMF that was set up to act as a proxy for the EAF environment. And this allowed us to feed material and film the material very easily with while studying what's going on in the steelmaking slag world, and examine the effects of bridging and the activity of the gases. And you can see with the carbon-bearing materials, you get a lot more activity in the slag and the foaming. And this is one of the big challenges that needs to be overcome with hydrogen-reduced DRI, is that it doesn't provide that source of gas evolution that causes enhanced stirring and enhances the foaming in the slag in the electric furnace environment. And so other means of controlling that have to be developed. Finally, we did a TEA analysis of the overall production process to evaluate the costs and the potential operation conditions for cost parity with natural gas with the use of hydrogen. And this shows the overall flow diagrams produced in MetSim. These were done by NREL, and they collected information about the operation and operating cost to produce essentially 1 ton of hot roll material or hot roll coil material, and the relative costs for utilization of hydrogen versus natural gas based on grid availability and electrolyzer load throughout the operating year of a typical weather cycle. And the bottom left actually shows what the cost of hydrogen has to be in parity with the cost of natural gas in these systems. And you can see that cost for hydrogen has to be pretty low, from under $1 per kilo to upwards to $1.8 per kilo if the natural gas price is actually high. So um, there is a lot of work to be done to produce hydrogen at those kind of cost levels still, but we have a pretty good feel of where we have to be in order to efficiently utilize hydrogen in the process. So with that, I want to open it up. Thank you, first of all, and thank you for putting up with my technical issues. And then I want to open it up to any questions. Does anybody have any questions they'd like to ask?
Okay. Well, if anyone has a question, please free to raise your hand and type into the chat, please.
It's a shy group.
I think so. Well,
Uh,
does anyone has
If the students don't feel comfortable with the English, we can help them translate their questions.
ok. Si alguno de los estudiantes no se siente cómodo hablando inglés, puede decirnos su pregunta en español y nosotros le ayudaremos a traducirla. Ok. So Leonardo Ibarra has a question. So if this project success, how long would it take to build a plant?
Very good question. I think we could build a plant today. The problem is we're not sure that we have the hydrogen infrastructure to supply it. And that's one of the advantages of a GISH reactor type system is that you could build the plant entirely to operate on natural gas and then utilize hydrogen as it becomes available. You know, there are, DRI plants are being built in many places in the world right now, and many of them are being fitted to actually utilize hydrogen. So I think from that standpoint, it's entirely feasible. What I would say is the use of the hydrogen DRI is very much also dependent upon how you plan to operate the electric arc furnace. And do you want me to pause at this point? Do you want to translate or?
Oh, okay.
I think we can go on, you said.
Okay.
Yeah.
No problem.
We'll
Perfect.
translate
Yeah.
the answers, the questions from the students, and then you can go on with your English. That's great.
Excellent. Excellent. So the other thing I wanted to say is we still have to figure out what the best way is to replace some of the benefits of slag foaming provided or generated by carbon-based DRI materials, right? Or other carbonaceous bearing sources like pig iron, right? And that might involve the injection of things like biochar or other things that can still be ultimately carbon neutral. So let me look at, see if so, how long would it take to build a plant? I study hydrogen and biomass co-injection. That's excellent. Excellent. Do you have any ideas for the methods that you may use to increase stirring during the process? Yeah, so I have a couple of different views on that. One is that there are big differences in stirring in general between AC and DC EAFs. And I am a fan of DC EAFs because the current flow through the bath actually induces stirring and actually enhances some of that mixing that you need in the process. The bigger question is how do you generate foaming? And that's going to today either take an alternate carbon source that is, a bio source, and that is the path that folks like Hybrid at SSAB have taken. Or we develop other methods to foam. And, I've actually had in my mind that it might be feasible to foam with hydrogen, in fact. There's some evidence in literature that that could be done as well. So let's see. Any other questions?
¿Tienen otra pregunta? Ok, el capítulo El Sol en Mano, adelante.
I
Hey,
see a hand
doctor.
raising. Yes, sir.
Thank you for your lecture. It's really a good, uh, um, oh, I forgot this word, but it's really a landscape of all the investigation of Missouri Science and Technology and the Paisley Steel Manufacturing Research Center. And I have a question about the most difficult challenge in this. I I don't know if I can say this. I don't know if I can say this, but it's the new way to make the steel with the hydrogen.
Yes.
But
Yes.
uh, I have a big question.
Okay.
Uh, Sometimes I saw the EIF with the hydrogen, and I have a question because when you do this reduction of the FeO with the hydrogen, you need to produce water, right?
Yes.
And what about the refractories of the furnace? That's something that I don't understand really well. You know, I know if you can answer my question.
Yeah, yeah. Let me attempt to. We have certainly thought about this a lot, and a number of people have been concerned about what happens in the presence of water vapor in a system, not only in hydrogen steelmaking, but hydrogen consumption, right? Or hydrogen reheating, for example, particularly in reheat and tunnel furnaces. And what I can tell you is, if you look at the water content, of hydrogen, of course, the product is 100% water, but the water contents are still pretty high in natural gas. You've got four hydrogens to the one carbon, right? Typically. And so even there, the water contents are high. The key to managing this uh, um, is to ensure that water doesn't condense in the backup systems of the refractories. We've seen very little evidence that water exposure to a lot of the refractory systems that are used in vapor form creates a problem, you know, at elevated temperatures. Now, water exposure at when the refractories are cool is a completely different animal, right? But during operation, we've seen very little evidence of degradation. Um, so I think it's a lot less of a problem that people think. The other issue with hydrogen, off-gassing is we have many steelmaking processes that utilize uh, uh, hydrogen and even water in the steelmaking process. I don't know if you're familiar with the AOD process, which is argon oxygen decarburization. There's a competing stainless steelmaking process called the CLU process, which instead of injecting argon, injects steam into the bath. And the steam is not dangerous as long as it's not condensed form of water, right? And
Okay.
that process actually operates, and you know, as I said, it's controlling the condensation of the water to make sure it doesn't get back to the liquid steel is the big challenge that needs to be addressed. And that's something that can even happen with natural gas injection. So
Okay. Now I have another question.
sure,
Uh,
please.
uh, because, well, we have two different types or inclusions in the steel, right? The endogenous and
Yes.
the exogenous. But what about the endogenous inclusions in this process without oxygen, and you put hydrogen instead? So what happened with these inclusions? Because you don't use silicon or aluminum to desoxidize. What is this this change in this kind of topics of the steel?
Well, if we're going to, make steel in the electric furnace, that is always going to be an oxidizing environment, right? It has to be. So, if you look at electric furnaces, they're tapping between 400, 1,000, or 1,100 parts per million dissolved oxygen, right? And that's really important for reactions like dephosphorylation. So unless you want to melt steel and not refine it, you're probably going to always be running high oxygen conditions. And that's where you probably will still need some carbon in the system, whether that's derived from biocarbon or other sources. The hydrogen influence on the inclusions is actually a pretty interesting question. And I've not studied the reduction potential of hydrogen in those environments, but I've not seen much evidence that at steelmaking temperatures that it has a big impact. Because, in the end, hydrogen has a limited solubility in the steel at steelmaking temperatures, right? And, you probably will never get above 14 ppm without it outgassing anyway. So whether that's enough to do some reduction, I suspect it's completely benign if you're aluminum killing. It might have some impact on FeO emulsion inclusions or possibly even manganese silicates. And I'd have to investigate that further.
Okay. Okay. And I have another question because, well, sorry, but it's
No,
really
this is why I'm here.
an enjoyable
I'm happy to do this.
thing for me. And I have a question about these fibers you mentioned earlier in this lecture, because you can check the oscillation, right?
Repeat your question. I wasn't sure I got it.
Okay. You in this lecture earlier, you present the fiber.
Oh, yes. Oh, yeah. We're doing a lot of work in that area. So let me back up.
Yes.
If I can. So the fiber optics, we are doing a lot of work right now in this area, instrumenting various molds to map the thermal behavior. And I showed an example. Here we go. So here's a small mold in our laboratory where we can do mold oscillation simulations. And what we do is we thread the fiber through the mold, and that one fiber gets continuous temperature measurements, that we can, map to a thermal map in each loop. And so if I play that, well, let me go back. If I play it, what you'll see is all of that data, about every half a millimeter along the fiber length, is collected from a single fiber. So you can imagine the mapping densities that we can do on molds these days. And we're honestly doing a lot of that work. We're currently, I have a student working out at US Steel right now that is actually using their mold oscillation simulator, and you're using fibers at multiple depths to try to directly measure heat flux, for example. We're also directly measuring, the heat transfer during the oscillation cycle. And I'm just starting a program now where we're going to attempt to put these types of fiber optics in a continuous casting mold at Nucor Sedalia. This is one of the high-speed micromill octamold designs that runs in excess of 8 meters a minute. So
wow.
So yeah, the fibers. You may have seen a lecture I gave when I gave the Howe Memorial Lecture, and the thermal maps you can derive from these fiber optics is just incredible. We're finding lots of applications for this.
Wow. I already saw this in the, I don't know if you know about Expo Acero here in Mexico, the AIST Mexico event.
Oh yeah, yeah.
Yes, but this year I saw this kind of optical fiber in this company. I forgot her house,
Okay.
Electronite,
Yeah,
and
Harass
it's
Electronite.
really it's
Yeah.
that's the first time I already saw this kind of instrument in the steel, and
Excellent. Excellent.
you can check the two temperatures or
Yeah.
only the steel temperature or
Well,
the slag.
so the technology that Harass Electronite has feeds a fiber into the steel in the electric furnace or in the LMF, depending upon the application. And they're actually, because they know something about the feed rate, they can actually interpret the temperature rises going through the slag and the steel to actually get slag thickness as well.
Wow.
Now, I'll tell you a little secret. We're working with Harass Electronite to couple their technology with our Raman technology so that we have the potential to do real-time slag analysis as well. So that's something we're
Wow.
working on currently.
Wow. It's really, really interesting about I am really interested about this field because it's all a new challenge in the steel.
Well,
There are a
absolutely. Go ahead.
I'm sorry, there are a couple of questions in the chat. One
Yes.
is
Oh,
by Dr. David Hebert, who
Yes.
first would like to congratulate you on your work and thank you for the presentation. He asked whether you have any predictions about the production scale.
Yes. Again, a very good question. Um, you know, in the US right now, there has been, some changes in, let's just say, government policy that probably will slow the implementation of this a bit. In fact, I've seen some of the big projects, I think, have been backpedaled because Cliffs was going to do something at Middletown, and I think SSAB was going to do something in Texas, and it looks like both of those programs have kind of slowed down for now. So I don't know. My guess is that the first production operating plant will probably still happen in Sweden, where either hybrid or whatever H2 green steel is now called. I forget what its name is now, but it has a new Swedish name. But I'm guessing they will still be the first ones, and they're probably a year or two out yet.
Okay, by the way, I forgot to mention that Mr. Hebert is studying hydrogen and biomass co-injection in blast furnaces. So that might be,
Yes, excellent. I think I saw that in the chat, so I
yeah.
think that's great. So there's a lot of interest in particularly biocarbon injection. In the EAF, it's all about being able to appropriately utilize that. And in fact, one of our application areas that's really interesting is that we've fiber optic instrumented injector panels. So one of the things we can do is monitor the temperature of the panel and tell whether when we're injecting carbon and natural gas and oxygen, whether we're getting blowback um, or whether we're getting direct radiation exposure. So it tells us a lot about the dynamics of foaming in the furnace. It tells us a lot about, scrap distribution and the potential for blowback and doing sidewall damage. And it's another really interesting application. That same application is also being used to detect water leaks in that environment too. So,
Thank you. And this next question is by Ms. Grecia Alvarez,
yes.
who would like to know whether you have any ideas for the methods you may use to increase steering during the process.
Okay. So the stirring, I will comment. Um, if you're an AC furnace, if you go to Europe, most AC furnaces, and especially the big ones, use bottom stirring or electromagnetic panels to stir. In the DC furnace, you get natural stirring because of the current flow. And so there's very minimal benefit to stirring in a DC furnace compared to an AC furnace. So, DC furnace technology is one approach. Gas, stirring is another approach. I've traveled through Europe, but I've seen stirring done by uh, bottom tuyeres, bottom porous plugs, and electromagnetic stirring panels in the bottom of the furnace. I think that's a technology that's being used on the very large furnace at Arvedi in Italy, for example. And I think that's a 450-ton furnace, a very large furnace. Does that answer the question? So I was going to mention this one slide that I put up here that shows the vibration. One of the things that we've been able to do is use optical strain gauges on continuous casters and daisy chain the sensors on each roll location in the caster. And because you can daisy chain these, you can instrument a whole bank of rolls with one fiber. And we have successfully been able to detect the position of the liquid core in the machine by the ferrostatic load shift and its effect on the support structures. So you can see a deflection when liquid core passes under a particular roll set. But unlike using traditional strain gauges where you have to supply power at each point and you have to have individual signals back from each strain gauge, we use a single fiber and we place two FPGs on the fiber on the each beam and then string them together and multiplex them for a single fiber signal, very low cost instrumentation environment for detecting liquid core. And that's really important if you're running casters where you want to control dynamic soft reduction, improve centerline segregation and the like.
Okay. Well, if we don't have more questions, I would like to thank you very much, Dr. O'Malley, for such an inspiring presentation. We deeply appreciate the time you have taken to share your expertise with us and for offering such a very valuable perspective of hydrogen steelmaking and cutting-edge research being carried out at Missouri Science and Technology. Your lecture has not only expanded our technical understanding, but also motivated many of us to continue exploring the changes and innovation shaping the future of the steelmaking. As token of our appreciation, we would like now to present a certificate of recognition to Dr. Roland O'Malley on behalf of the AIST student chapter for his outstanding contribution to this academic session and for his continued support for students' engagement in metallurgical research and education. Thank you once again, Dr. O'Malley, for your generosity and for inspiring the next generation of metallurgical engineers.
Thank you so much. I will also offer that if people have questions or need help with anything, please feel free to contact me. I love engaging the students, and I'm just very proud to see such a healthy chapter in Mexico, and want to do everything I can to support it. So, thank you so much.
Thank you very much, Doctor. So, to all attenders, thank you for joining us. We invite you to stay connected with the AIST-ESIQUIE chapter and continue participating with upcoming technical talks and academic events. So have a great day and see you next time. Thank you.
Thank you, guys.
Thank you, Doctor.
Thank you.
Thank you to everyone.
Take care.
Take care, please.
Take care, Doctor.
Thank
Bye-bye.
you. Bye-bye.